Heyo, happy Saturday. Let's talk about intervals of convergence. But before we do that, let's just decide which of these series converge. Take a look and see if you can figure out which of these series diverge. Gut feelings. Okay, so we're going to look at three simple tests you can use to figure out whether or not series converge or diverge. Mostly, I think these are common sense. All right, so the first test is the nth term test. All you do is you see, are the terms approaching 0, or are they getting larger, or are they approaching a finite value? In this series, the terms are getting larger, so obviously the series has to diverge. In more mathematical language, you can say that the sum of the series diverges if the limit as n approaches infinity of the nth term does not equal 0. So in other words, if the terms are not approaching 0, your series has to diverge. And in this series, we know the terms are getting larger because the numerators are exponentials. It's 2 to the n. And the denominators are square numbers. So what about the converse? What if the nth term is approaching 0? Does that mean that your series has to converge? No! That top series diverges, even though the nth term is approaching 0. But the bottom series still converges, and the nth term also approaches 0. So I think the moral of this story is if the nth term is approaching 0, you just don't know about your series. You have to use some other test to figure out whether or not it's converging. Okay, so let's do another test. This test is called the ratio test. You're going to look at the ratio of the n plus first term over the nth term as n approaches infinity. And if that ratio is smaller than 1, your series is going to converge. And if the ratio is larger than 1, it will diverge. And if it equals 1, then again, you can't tell. You have to use a different test. So let's look at an example of applying the ratio test to this series here. So you see, I've got there the n plus first term, that's 1 over n plus 1 factorial, divided by the nth term, that's 1 over n factorial. And I invert and multiply. And I can simplify it to get just 1 over n. So the limit of that ratio as n approaches infinity equals 0. Because the limit of the ratio equals 0, I know that the series converges. What does it converge to? Does it converge to 0? Definitely not, because obviously we start out with the number 1, so that's already more than 0. You don't know what it converges to. These tests don't tell you what it converges to. They just tell you that it doesn't go to infinity or negative infinity. Okay, what happens if we do the ratio test with this one that I told you didn't converge? Same thing. I've got the n plus first term over the nth term. I invert and multiply. And the limit of n over n plus 1 as n approaches infinity is just 1. So this was the situation I said where this test doesn't tell you whether or not it converges. So we need another test. All right, test 3. This is called the integral test. The integral test is you just think of your series as an RRAM or an LRAM approximation for a particular integral. So in our case, we can think of it as an LRAM approximation for the integral from 1 to infinity of 1 over x dx. We already know that that particular integral diverges, and it's pretty clear that those rectangles, the area in the rectangles, is larger than the area under the curve for that integral. So since the integral diverges, we also know that the series has to diverge. So that's the idea. You can go both directions here. So let's say that S is our sum. If S is larger than some integral that diverges, then S has to diverge. But if S is smaller than some other integral which converges, then you know that your sum also has to converge. Okay, what's that K about down there at the lower bound of integration? You saw in the last slide that we can start this sum, we can fit the sum into the integral wherever we want to. In this example, I started it at 1, was the lower bound of integration. K just means that you can start your integral wherever you want, so long as the inequality holds. So as you can make K whatever you want, so long as S is greater than the integral that diverges, or so that S is smaller than the integral that converges. Okay, so that's all the tests. Here's a summary. you've got some series. Does it converge or does it diverge? First, look at the nth term. If the nth term isn't approaching 0, it's got to be diverging. Okay, if the nth term is approaching 0, then look at the ratio of the n plus first term over the nth term as the limit of n approaches infinity. If that's less than 1, it converges. If it's more than 1, it diverges. If it's equal to 1, then try to compare the sum to an integral whose area you know. Okay, so why don't you go ahead and check out the handout that I gave you, the notes for section 9.4, which is radius of convergence. I'm also just reminding you this fact that you already know about geometric series here. Look at these problems, 1 through 6. First, look at each one and just decide yes or no, can you use the nth term test for divergence to see if it diverges? I'll give you a hint. Exactly half of these you can immediately show that they diverge using the nth term test.